Hi class, we continue our study in chapter 12 talking about circles and other conic sections by moving into section 12.2, which is about chords and arcs. So in this section we have two objectives. We want to use congruent chords, arcs, and central angles, and then we finally want to use perpendicular bisectors to chords. All right, so first off, what is a chord? A chord is a segment whose endpoints are on a circle. So the diagram shows chord PQ and its corresponding related arc. Remember, the arc sign is not showing up in these PowerPoints, arc PQ. So we have chord PQ, right, which is the segment here, and arc PQ. So a couple theorems, all right. This is about congruent central angle and arcs. So theorem 12.2.1. So within a circle or a congruent circle, congruent central angles have congruent arcs. So if angle AOB is congruent to angle COD, then the arc AB and CD are congruent, and then the converse is the same, right? So if you have congruent arcs, so if AB is congruent to CD, then their angles here, central angles, are also congruent. That makes sense. Another one, theorem 12.2.3, within a circle or a congruent circle, central angles have congruent chords. So if this angle here, AOB, is congruent to angle COD, then chord AB and chord CD are congruent, and then its converse is also true. So if chord AB is congruent to chord CD, then these angles here are congruent as well. All right, theorem 12.2.5. So within a circle or in congruent circles, congruent chords have congruent arcs. All right, so obviously if chord AB is congruent to chord CD, then arc AB is congruent to chord arc CD, and then its converse is the same. So if arc AB is the same or congruent to arc CD, then chord AB is congruent to chord CD. And I think all those theorems make sense. All right, so let's talk about using congruent chords. So in the diagram, circle O here we know is congruent to circle P. If we're given that chord BC is congruent to chord DF, what can you conclude? Well, you can conclude two things. First, you can conclude that angle O here and angle P are congruent because within congruent circles, congruent chords have congruent central angles. And then also the measure of arc BC is congruent to the measure of arc DF because within congruent circles, congruent chords have congruent arcs. All right, two things we could conclude from that. All right, some other ones. So theorem 12.2-7, within a circle or in congruent circles, chords equidistant from the centers or centers from the center or centers are congruent. So here we have OE is equal to OF. What that's saying then is that chord AB is congruent to chord CD. And then also its converse within a circle or in congruent circles, congruent chords here are equidistant, right, from the center. So if chord AB is congruent to chord CD, then OE is equal to OF here like that, right? Long as where they meet, this is important, are 90-degree angles. Because like if you have a chord up here, it wouldn't meet at a 90-degree angle, right? Or a segment here that goes up. So as long as they meet to form 90-degree angles, they're congruent. All right, so another one here. So what is the length of RS here, right, in this circle? Well, notice how they meet to form 90-degree angles, right? So recall that chords equidistant from the center of the circle are congruent, right? And I can tell they're equidistant because they each form 90-degree angles and the measures are 9. So thus, PR is equal to RS, right? So let's find PR here, right? And we'll use that to have RS then. Well, I see that PQ is equal to QR because they're congruent. They're equal to 12.5. So it's really the same thing here. So 12.5 plus 12.5 is equal to PR, and PR is equal to 25. And we know that RS, as I said, is equal to PR. So RS there is equal to 25. Oh, that wasn't too bad, right? So the length of that segment is 25 units. All right, so another theorem, theorem 12.2-9. If in a circle, if diameter is perpendicular to a chord, all right, then it bisects the chord and its arc. So if AB is the diameter and AB is perpendicular to CD, like this, then what we can say is this chord, or this segment CE and segment ED are congruent, and the measure of or arc CA is congruent to arc AD, like that. Another theorem, if in a circle, if a diameter bisects a chord that is not the diameter, right, then it is perpendicular to that chord. So if AB is a diameter here, and then what we're saying here is any chord here that it bisects, CE and ED here, all right, and they're congruent, then we can say for sure then that they're perpendicular, that AB is perpendicular to CD, like that. All right, another one. If in a circle, the perpendicular bisectors of a chord, all right, contain the center of a circle. So if AB is perpendicular to the bisector chord CD here, like this, then what we know is then AB contains the center. It has to contain the center of the circle O. It doesn't tell us where, it just tells us that it has to contain the center. All right, so let's do two examples here. So given a circle, describe how to find the center of the circle and the length of its radius. So I just have this circle here. All right, so without the center of the circle J given, we cannot find the length of its radius. However, we can use an earlier theorem, 12-2-11, to find the center, believe it or not. This theorem says that the perpendicular bisector of a chord contains the center of a circle. All right, so what we're going to do is we're going to draw two chords. They cannot be parallel to each other, like this. Any two chords, it doesn't matter, okay? Next, construct a perpendicular bisector for each chord. So draw a line that goes through the center here, and another one that goes through the center there, like that. So this one bisects the first chord here, and this one bisects this other chord here. The center is located then where the two intersect of the perpendicular bisector. So right there, just like that. All right, let's do one last example. So I want to find the value, all right, what is the value of each variable to the nearest tenth? So I want to find the variable r here, right, from this. Well, the first thing I'm going to notice here is that I got a right triangle. So I want to find the measure of ln here, all right? Well, I know, all right, that if n there, all right, because it meets at a 90-degree angle right here, all right, from the center, that ln and mn are the same. So ln has to be half of 14 then. That's the only way that ln and nm can be the same. So it's equal to 7. So then I'm just going to use the Pythagorean theorem, since this is the hypotenuse. R is equal to 3 squared plus 7 squared, right, which is 9 plus 49 gets me 58. Taking the square root, we see then that the radius r there is roughly 7.6 units. All right, another one real quick. What is the value of each variable here, right? So y to the nearest tenth. All right, well, it might not seem obvious at first, but BE is congruent to BA because they're both radii. They're both radiuses here. So what I also see is that BC is perpendicular to AF here, like this. All right. So what I see here is BA is equal to BE, which is equal to 15, as I said. So just using the Pythagorean theorem, 15 here is the squared, is the radius. So y squared plus 11 squared is equal to 15 squared. So after I square 15 and subtract away 11 squared by moving it over, I just get y squared is equal to 104. So roughly when I take the square root, is y is equal to 10.2 units.